Hello and welcome to the first short paper session here at URBIS. My name is Michael Behrisch, and I'm an assistant professor for visual analytics working at the Utrecht University in the Netherlands. And I'm honored to present to you today in total 8 cutting-edge short papers. Our session is entitled Analytics and Evaluation and deals with topics that are generally related on improving the visual analysis and proving that visualizations really help in the structured analysis process. For the next 90 minutes, we will see in total 8 pre-recorded presentations, each being around 8 minutes long, and each paper gets afterwards a short live Q&A session in which I will restate your questions according to my understanding. And if you think about this should remind you a little bit about the child game Chinese Whisperers. So please be so kind and state your questions very explicitly so that you can really get the answer that you want. Which brings us to the how. The rules of engagement for today are that you can either ask your questions here in the live chat or in the Discord channel that is dedicated to this session. And for the Discord, we will have the thumbs up functionality that will help me to see what interests you as the audience most. So please use the thumb up functionality over there and feel free to follow up with any questions on that with the authors respectively through the channel in Discord. And with that, we're going to jump right into our first short paper with the title, The Effect of Graph Layout on Perception of Graph Properties by Electra Kypridemou, Michel Cito, and Marco Bertam.
Hello, my name is Electra Kypridemou, and this is a joint work with my supervisors, Dr. Michele Zito and Dr. Marco Bertamini from the University of Liverpool. In this study, we examine the effect of layout on the perception of graph properties. In today's world, lots of information is displayed in the form of graphs or networks. As an example, here we can see a network of recipes and their ingredients and how they are connected. The way we choose to represent a graph visually is crucial for understanding the properties of the graph and for making decisions. In the graph drawing literature, there are many graph drawing algorithms that generate such visual representations automatically. Usually, the quality of these algorithms is evaluated based on some visual characteristics of the drawing that are found to affect the human perception of the graph and make the drawings more aesthetically pleasing, more usable, or more readable by humans. Recently, Sony et al. Studied how these different layouts affect the user's ability to perceive some properties of the graph. They used graphs of 100 nodes each. Participants viewed 2 graphs of the same layout and had to select the one that was more dense. Here, for example, we can see that the graphs on the right side are more dense than those on the left side. But what if we asked about which of the 2 is connected, or which of the 2 is a tree? It would probably be impossible to answer such questions on large graphs. This is why we extend this work by studying smaller graphs of 16 nodes each, including certain properties that can only be perceived in lower order graphs. So, in this study, we examine how the different layouts affect the perception of specific graph properties on small graphs of 16 nodes each. We choose to study 3 very different properties of graphs, the connectedness, treeness, and density, which I'm going to explain in a bit. We also choose 4 layouts, the circular, grid, planar, and spring. For the first 2, the nodes are assigned to random positions in a circle or in a grid respectively. For the planar layout, the graph is drawn in such a way so that no 2 lines intersect. Since not all graphs can be drawn in such a way, we had to restrict our study to planar graphs. Finally, we have the spring layout, which is under the family of the force-directed layouts. The general idea here is that all nodes repulse each other so that they are evenly distributed in space, but in addition, connected nodes attract each other. Here is a small sample of the experiment. Participants viewed the 2 graphs of the same layout displayed side by side on the screen, and they had to select which of the 2 had the desired property. There was a fixation cross on the screen, after which the two layouts appeared and remained on the screen for 3 seconds. Then there was a prompt screen until the user submitted their response using their keyboard. In total, there were 48 trials for each task, and the position of the target graph was balanced across the trials. For our experiment, we designed 3 separate tasks, one for each graph property. For the connectivity task, participants had to select the graph that was connected, meaning that every node is connected to every other node with a path. So in this case, the graph on the right is connected. For the tree task, they had to select the tree. A tree is a graph that is connected and has no cycles, so in this case, the one on the right is a tree. For the density task, they had to select the one that had more edges. Here, one graph always had 16 edges and the other 18. In this case, the more dense is the one on the left. So, for this experiment, we recruited 24 participants with no background in graphs, which were assigned into 3 groups of different task order. We provided detailed instructions explaining the properties and the tasks. For each task, before the actual experiment, there was a training phase of fewer trials to familiarize participants with the procedure. During the training, we also provided auditory feedback. After the training, we asked participants to report their confidence about the procedure. After ensuring that everything was sufficiently explained, they proceeded to do the actual experiment. At the end of each task, they answered 2 open-ended questions regarding their strategies. Moving to the results. Here you can see a comparison of the performance between the 3 tasks. Performance was significantly different than chance in all cases. So participants performed all tasks in a meaningful way. Also, there was no significant main effect of the task, meaning that the 3 tasks had similar level of difficulty. Moreover, there was no effect of the group, so the order of the tasks did not affect the performance. Then, we analyzed each task separately. For the connectivity task, the planar and spring layouts resulted in significantly better performance than the other 2. This is probably because these 2 layouts tend to draw the 2 components of the non-target graph separately. Moreover, the spring layout, in which the 2 components are drawn in distance, clearly outperformed the planar one. The circular and grid layouts, on the other hand, resulted in performance not significantly better than random answering. This is probably because in these 2 layouts the 2 components intersect and hence they are not visually separable. Based on the results, one could imply that when the 2 components are drawn separately, the distance between them seems to be a good predictor for the performance. And when the 2 components intersect, the task becomes much harder. For the tree task, it looks like the existence of cycles in the drawing mainly guided the participants when selecting the tree. This was also evident from the questionnaires. The pattern of the results here is similar to the connectivity task. The planar and spring layouts resulted in significantly better performance than the other 2. Moreover, the spring layout outperformed the planar, suggesting that the clear demonstration of the cycle facilitates performance. Similarly to the connectivity task, the circular and the grid layouts resulted in performance not significantly better than random answering. This is probably because of the large number of edge crossings, which make the drawing misleading regarding the cycles of the graph. So we can say that drawings with fewer or no edge crossings make the cycles of the graph more visually prominent. So when there is a cycle, you can more easily find it, while drawings with larger numbers of edge crossings are usually confusing regarding the existence of cycles in the graph. Finally, for the density task, all layouts resulted in performance better than chance, and no layout was significantly better than the others. This result is consistent with the previous study from Sony et al., where comparing 3 different layouts, there was no significant difference in performance when perceiving the density. So to sum up, we can say that the layout affects the perception of graph properties also in small graphs. Among the layouts that we examined, the spring layout seems to facilitate perception, but not for all graph properties. And as future work, it would be worth examining how particular features of the layout might affect the human perception of the graph properties. Thank you.
Great. Very interesting work, and also a very important direction, because I think personally that global density is not the only property that we should examine when it comes to graphs. And I see also quite some relations to the related work in the last year's viz on better force direct layout, adjacent fields. I have to say that now, matrix utilizations. So there came up one question through the Discord channel, which is the correctness plot goes to 125%, and some distributions go over 100%. Why is that so?
Okay, this is just the way the violin diagrams are plotted. It's definitely not more 100%. It's just the way it's depicted on the graph. It's not so accurate. Yeah.
Okay, great. So coming a little bit to my questions that I had before, right? If we look at typical graph analysis tasks, then you see that there are these global tasks where you're interested in the density of the entire graph. But one other thing that strikes my attention is, what about these more local aspects, such as you want to find a cluster? How does your approach help me to find the right approach for globally sparse graphs and locally dense graphs?
Yeah, very good question. But this is very important. But this would need a completely another experiment to study, because in our case we just showed the two graphs for 3 seconds, so you don't really have time to explore the graph. It's just the first impression you get from it. So for such properties like the ones you said, you will need to design another experiment and let the user really explore the graph with maybe interact with it, but for sure give it a bit more time. Otherwise, you cannot really ask questions like this, I think. So yeah, maybe this would be a good point for the next experiment.
Yeah,
thank you.
Great. Super, thanks. With that, we're going to switch over to our next paper that has a very prominent collection of authors and deals with exploring time series segmentations using uncertainty and focus plus context techniques. The authors are Christian Bors, Christian Eichner, Silvia Miksch, Christian Tominski, Heidrun Schumann, Theresia Gschwandner from the TU Wien, and Uni Rostock. Here we go.
Welcome to our presentation entitled Exploring Time Series Segmentations Using Uncertainty and Focus and Context Techniques. This is joint work between the TU Wien and the University of Rostock. The main part of this work were done by Christian Bors and Theresia Gschwandner. Both are unable to give the presentation. Consequently, it's an honor to give it. My name is Silvia Miksch. What is our main motivation to handle this? We are dealing with multivariate time series, and with the we want to perform some segmentation and labeling. And usually we have different kind of parameter settings, and we have different kind of segmentation and labeling settings. And according to the different parameters that you see on this side, different kind of labeling can change it. However, these are parameter dependent, but we want to really explore it in more in depth. What is our main motivation to proceed? Uncertainty is everywhere in multivariate time array time series. Uncertainty is evidently introduced during the pre-processing as well as the modeling phase. And we want to provide an exploration environment which is uncertainty aware and take this high dimensionality into account. And we want to provide an interactive exploration environment to find segmentation results according to these different aspects. The challenges we are addressing is to finding a good segmentation result which consider the quality of the segmentation for particular parameter configuration, which takes the influence and the relationship of uncertainty of these results, individual timestamps or intervals into account, and the transaction characteristic between the different segmentation. Down here you see an example where you see in color coding the different detected time intervals or labeled. The color represents the labeling here, and here you see the segmentation detected after the time series over time, and down here you see the different probabilities for each time step. Let's consider our visualization design, and the basic requirement we want to incorporate is two types of uncertainty. The first one is value uncertainty, quantified from data collection or pre-processing. The second one is result uncertainty, for example, probability assigned by a labeling algorithm. And we are aiming for maintain a very compact view where we can incorporate all the different multivariate time series and the different uncertainty, and to communicate the uncertainty with limited vertical space. Our aim is to incorporate and combine result and value uncertainty and support the different analysis goals with respect to the analysis with respect to uncertainty inspection. Look at the different kind of overview visualization we provided for encoding result uncertainty. We provided a very compact overview about the different result uncertainty, which are represented in three different plots. One is the uncertainty heat map plot, the second one is the gradient uncertainty plot, and the third one is the threshold uncertainty plot. Let's consider first the uncertainty heat map. The uncertainty heat map plot gives an immediately impression of uncertainties only, no segmentation levels. We use a grayscale with light values exhibiting high result uncertainty. The second one, the second plot is the gradient uncertainty plot, which shows the different segmentation and labels together with the uncertainties. The default gradient uncertainty view uses color and transparency. And the third visualization is the threshold uncertainty plot, which enables a more directed exploration. This view shows only labels that exceed a certain probability threshold that is set interactively. This prevents visual clutter and facilitates the comparison of small differences between the segmentation results. One important component of our solutions are different kinds of interaction techniques. The first interaction technique that we provide is a row lens view to support the inspection of different types of uncertainty. In this row lens allows for vertically zooming a segmentation result of interest. In this example, the lens area is used for showing three juxtaposition views displaying from the top to the bottom, segmentation coloring, label probabilities as line plots, and the value uncertainty as stacked area plots. The parameter values are color highlighted and provide detailed information on mouse over interactions. The second interaction technique technique is a temporal lens which allows to magnify areas of interest for further inspection. In this view, we see a temporal lens that magnifies a segment boundary near the mouse cursor and shows the exact temporal change of label probabilities as a stacked area plot. We have evaluated our encoding of uncertainty in a quantitative in-between subject-user study. The study included 111 participants, and we compared the performance of the different uncertainty designs. We defined different comparison tasks and measured error rate and task completion time. In summary, the results are no disadvantage from adding uncertainty to existing encoding, and the gradient uncertainty plot is more effective than the threshold uncertainty plot for large number of results. More details can be found in the paper and in the supplementary material. Let's conclude. We presented you the design of visualization technique to support uncertainty-aware exploration of large sets of segmentations, and the design of an uncertainty-based lens exploration of results in overview visualization. Our results can be generalized to design visualization of similar uncertainty dimensions and features, similar space constraints and tasks. Thank you.
Yeah, great. Here we are again. I saw some comments in the chat. Yes, this is a clear link to Christian Struminski live keynote in the UVA session where he propagated or where he proclaimed that lenses are important and in situ visual analytics is important. Yes, for sure. This is one of the instances of this. So let's open up for questions. And while you're typing, my question is, one result that really struck my attention was that these gradient uncertainty plots outperformed the threshold narrative, right? Which is kind of an unintuitive thing for me because do you think that people easily live with vague statements in visualizations, but in real world they tend to avoid them?
Do you hear me? Do you hear me? I mean, the basic assumption for this is because we want to really emphasize on the uncertainty. Therefore, we emphasize on these aspects and not on the real aspects. This was the reason why the people like this more.
Great, thanks. So, in the interest of time, we are switching already over now to the next paper with a totally different topic, namely social media analysis. The paper is entitled SAMBA Design Study for Visual Analytics Tools for the Music Industry, powered by YouTube Commons. The presenter will be Victor Oliveira, and the authors are Christina Stoiber, Johanna Kuhlbauer, Christoph Musik, Alexis Ringo, and Andreas Gebelsmeier from the St. Pölten University of Applied Science in Austria.
I am Victor Oliveira from the St. Pölten University of Applied Sciences, and I will present our SAMBA, the design study of a visual analytics tool built for the music industry and powered by YouTube Commons. Data from comments on social media platforms offer valuable information about trends and market changes. Including the music industry, companies have access to tools for continuous monitoring of sales and web traffic. There are many types of social media monitoring tools for specific platforms and across platform. However, not every social media monitoring tool is focused on unstructured user-generated content, nor are they based on artists and songs in an open way. Therefore, we propose Smart Data for Music Business Administration Visualization, or SAMBA, as an extension of an analysis tool such as YouTube Analytics, which is artist and song based and focused on user comments. After getting comments from music videos on YouTube, we run different natural language processing algorithms and store the results on a local database. We then visualize the results on our SAMBA-Viz dashboard. The tool was developed as part of the SAMBA project, which is running since 2017. This project is funded by the Austrian Research Promotion Agency and includes researchers from the Department of Media Economics and Media and Digital Technologies from the St. Pölten University of Applied Sciences. During this process, we have run interviews with domain experts, explored methods for natural language processing, creating a database of comments, and designed our visualization dashboard, which was then assessed in a workshop and with further usability tests before the phase of documentation and dissemination. In this paper, we reported our first main points from our interviews until our workshop with experts. On our interviews, we counted with the participation of 5 domain experts, 3 representing indie labels, 1 representing a major label, and finally 1 representing a concert agency. All interviewers were male and reported having 10 years of experience on the business. All interviews have shown a strong interest in social media marketing. All of them report using Google to search for what kind of online presence artists have. They also report using conventional social media and also commercial social media monitoring tools. Social media monitoring was shown to be very time-consuming, so they emphasized that the tools need to be easy to use. Finally, the input from the public, as well as long-term trust in the data used by the tools, were shown to be crucial. The highlighted points represent our main design requirements. When applying such requirements to the design of our tool, it all starts with a search by artist or song, which can be triggered by a button on the top left corner of the page and shows the different versions of the desired music video. From that search, we select the videos we want to analyze and display their key performance indexes. To display the temporal development of the comments for each selected video, we use a line chart. Users can also read the comment directly on the dashboard. Finally, the text mining results are shown in different cards. Currently, cards in this area display information about language, engagement with comments, sentiment analysis, and topics. Each card includes an overview window, which aggregates data from all selected videos, and a detailed window grouping data by video. In addition, time filter can be applied using a slider or brush, which is reproduced on all other cards. To demonstrate the capabilities of SAMBA-Viz, we analyzed the video "We Are Going to Ibiza" by Venga Boys to observe the effect of the Ibiza affair, which was triggered by the release of a video of the former Vice-Chancellor of Austria, Strache, on May 17, 2019. In our dashboard, it's possible to see a peek of comments on the music video starting on the same day of the Strache video release. Most of the new comments were in German, and the main topic can be observed in our keyword list. In our next validation step, we performed a second workshop with domain experts at Musica Austria, MICA, in June 2019. We had 14 participants from 23 to 55 years old. Their expertise varied between arts, musicians, managers, social influencers, and one expert on the music business in Austria. They were asked to perform different tasks with the dashboard. Results show that it was easy to find and compare data from different music videos. However, many errors were done regarding visualizing time data and applying the time filters. Participants were also not familiar to the use of a brush. Although they needed improvements, the dashboard yielded an average of 73 points on the SUS, revealing an already acceptable usability. Our evaluation focused on the Austrian music industry. Yet, many of our data mining tools were optimized for English content. Besides, we didn't explore more advanced types of visualization as the music professionals were not visualization experts. Finally, defining requirements for the domain experts of our tool was a challenge, as our users can have different roles, such as being managers, artists, and social media influencers. In this presentation, we briefly report our participatory design process, as well as a user scenario and the results from a final workshop with experts, which shows how SAMBA-Vis can support assessing data from comments left in music videos on YouTube. Our final assessment shows that SAMBA-Vis is usable and effective for professionals in the field, but further improvements are necessary.
Great, thank you. Very interesting paper. Let's open up for questions. In the meantime, I will just ask a very short one that is related to the natural language processing part, right? Can you track which feature or part or section the audience really liked or disliked, which has really clear applications for product feature analysis, and this is of great interest for the commercial field.
So when we are doing the workshop at the end with the influencers and artists, the thing they liked the most was the sentiment analysis, because they said they could not easily find on tools, especially the ones that are free. So in our dashboard, for instance, these was the ones that were below. So you could find sentiment and topics, and they said those should be the main things to display because they were the most interesting.
Great, thank you. I don't see any other questions here, so I will just move over to the next one. Thank you very much for this interesting paper.
Thank you.
The next paper will have also a business-related aspect and will show us how we can buy our next laptop, a process that I typically struggle with. And the paper is called Configuration Finder, a tidy interface, visual interface for effective perceptive search by Patrick Riemann, Andreas Schädler, Jannis Harder, Jakob Herpel, and Bernd Fröhlich from the Bauhaus University Weimar. And with that, the stage is all yours.
Welcome to my talk. My name is Patrick Riemann. I'm with the Virtual Reality and Visualization Research Group at Bauhaus Universität Weimar, and I'm going to talk about the configuration finder. Faceted search interfaces are typical for web shops. We conducted a web shop survey according to Marty Hurst's guidelines for search interfaces, as well as some additional guidelines we came up with. Sadly, the results are quite poor in general, yet the most annoying problem that one can't see how the listed attribute values are related to one each other and which combinations might appear. Showing a notebook dataset with its typical attributes as CPU, price, vendor, and so on in a parallel coordinates plot provides all available attribute combinations at once, but of course suffers from clutter and overplotting when depicting so many products and their many attributes. Some years ago, the Product Explorer reduced the number of axes based on importance and with help of an axis repository. But still, the many individual lines can be quite confusing. Of course, binning records according to the attribute values, as with parallel sets, is one solution, but becomes also cluttered with an increasing number of attributes and actual existing attribute values. Keck et al. Developed a system where you can entirely switch back and forth between parallel sets and parallel coordinates, which does not exploit the potential of combining both. Our configuration finder actually combines both paradigms in order to provide a tidier display. Proxy axes represent a set of related axes. We use appropriate combinations of set-based and individual connections. And we also suggest fusion axes, which allow merging of two separate axes. A single proxy axis represents a set of semantically related attributes. Here the GPU vendor axis represents further attribute, such as the name of the graphics card, the amount of RAM, or the type of RAM. A closed proxy axis indicates the sub-axis by distinctive icons below. Opening this axis reveals them as real axes within the proxy axis. That is actually split vertically in half, as you can see on the left and on the right side. Besides sub-axis, a proxy axis can also contain other proxy axes, such as the screen proxy axis that can also be expanded by adding another level to our hierarchy. As a second step, we reduce the number of connections according to the individual axis pairs. It makes sense to treat scalar or continuous attributes with only a few existing attribute values as categorical axes, such as HDD or memory. However, of course not the price, where we prefer individual lines instead. As soon as the first attribute value is chosen, the connections come into play, in order to show quantitative relations as ribbons between categorical axes and individual curves between categorical and continuous axes. Choosing an attribute value of a sub-axis is done in the same manner and affects the global filter as well. Particular attribute is highlighted by its colored icon. Choosing an i7 processor and an NVIDIA graphics card quickly narrows down the result set. But one of them is out of our budget. But a cheaper one might be a candidate for us and is highlighted as such, overlaying all other curves and ribbons even when adjusting our requirements to reveal other potential laptops. In order to reduce the number of visual elements further, two axes can be combined, such as categorical and categorical axes. By presenting the attribute value combinations, which are intersections of the value sets of axis A and B as sub-areas in the areas of axis B, according to the numbers of those attribute combinations. For example, when applying the categorical axis GPU to all other axes, the subsets AMD, Intel, and NVIDIA are shown as respectively sized visual sub-areas on all value areas. A selection of the entire value area remains possible, but sub-areas can be directly selected. Combining a continuous and a categorical axis is similar. All products that have a particular categorical value of axis B are gathered, and the distribution regarding the quantitative attribute A is mapped by color onto that value area. All areas look different depending on the actual values. Applying a quantitative attribute, such as price, to all categorical axes reveals additional information about the distribution of the price ranges within the value areas. Of course, the i7 and the 64 GB areas contain the darkest colors, since those products have the highest prices. Selection is directly possible by simply brushing on the desired range on a value area. The selected range can then easily combined with regular selections or deselections of other value areas. In a pilot study, we compared our system to a fully functional re-implementation of a webshop interface, top ranked in our webshop survey. The results showed a clear preference of the participants for our system. They stated being more confident using our system and that it appeared to be more trustworthy. Furthermore, we conducted an expert review with 6 experts that are with one of the very first companies providing commercial webshop systems. Also here, a brief demonstration sufficed to enable our experts to perform example tasks as well as narrowing down their own laptop requirements and interests. The review turned quickly into some kind of a market analysis situation in order to find typical relations and missing configurations no webshop offers. Our experts also saw potential as an in-house application to compare a company's portfolio against the market or for optimizing in-house purchases. They especially liked the Fusion axis for combining price information with any other categorical attribute in that regard. While our web-based implementation renders with JavaScript solely on the client, it already scales to thousands of products with more than 40 attributes. Even larger datasets would require aggregation techniques such as clustering very similar products into a single one. However, when continuing the work with our experts, we have to find out how to integrate those features into regular webshop interfaces. Thank you.
Thank you very much. Very powerful concept of hierarchical and fusion aggregates that have totally different data types, for example, categorical and quantitative. So the question from Wolfgang Eitner came up, how do you deal with access reordering?
So currently access reordering is possible, but not interactively. So in principle right now, the hierarchy and the setup is curated, so you have to define them. So of course, one challenge for the future would be creating these semantical relations based on the data, and then also allowing interactive reordering from in the visual display, but also grabbing an axis that is a sub-axis within another axis and then bringing it to the top level is also a useful feature that we would like to implement in the future.
Yeah, fully understandable. Makes it definitely worthwhile following up on that. So the next question that came up is a parallel coordinates plot is quite a complex visualization. How did you explain it to the users? And did they have difficulties in understanding? Once again, a question from Wolfgang.
So the crucial thing, we start with a very tidy display. That means before you select the first attribute value, you do not see any connections at all. So and I'm convinced that makes it easier for the users to assess the situation, to see the attribute axes, and get an understanding what is the data space or the visual data space I'm dealing with. So the first thing we told the users also in the user study was, okay, you see a vertical axis and this is one attribute of a notebook. And as soon as this clicks, so it's quite easy for the users. And then once they are familiar with the interface, they click on an attribute value, and then after that, immediately the connections come into play, and they are not surprised by that, nor they are overwhelmed by a visual cluttered display that they have to deal with from the starter. So I guess this was one. I didn't mention that, or I didn't feature that so much in the talk, but I think this is also a crucial point. So starting without any connections at all, in order to guide the user more.
Yeah. Hey, Patrick, great work. Looking forward to seeing this real online, real web shop interface. And I'd like to hand over now to the next paper, which is an honorable mention short paper. It's called Argus Interactive Visual Analytics Framework for the Discovery of Disruptions in Behavioral Rhythms. The presenter will be Hamid Mansour, and the stage is all yours.
Hello everyone, my name is Hamid Mansour and today I will be presenting Argus, Interactive Visual Analytics Framework for the Discovery of Disruptions in Biobehavioral Rhythms. This work was made possible by a grant from DARPA. Context-aware computing, in which a device like a smartphone makes inferences about your context, that is, your location, activity, etc., has the potential to improve healthcare. Biobehavioral or circadian rhythms that represent how regularly people perform activities such as sleeping are important health markers. Such rhythms and their disruptions can be detected using continuously collected smartphone-sensed data. While computational models are able to sense behavioral disruptions, they provide little insight into their causes. Representing smartphone-sensed rhythms using intuitive visualizations can help analysts like behavioral experts explain disruptions in them which have health ramifications. There needs to be some metric to quantify the level of overall rhythm in a person's data and breaks therein. We conceptualize smartphone sensors as channels of contextual information. Channels are sequences of binary indicators such as activity, still versus walking, or sensor readings, phone locked versus unlocked. Deviations from detected rhythms in the different channels may be indicative of a biobehavioral rhythm disruption. Our three categories are geolocation, phone state measurements, and activities. We applied the Lomscargill periodogram to each channel of the data to find the underlying daily periodicity or circadian rhythm and converted that to a score for each channel category. We present Argus, an interactive data visualization tool to find and explain biobehavioral disruptions as detected from smartphones. The first view on the left is the eyes of Argus view, which represents the rhythms detected for all users across all days. Each circular glyph represents one user, and the purple line encodes the rhythm deviation score for every day of participation ordered clockwise. The black circle represents the average rhythm values, with larger circles indicating stronger overall rhythm in the person's data. The closer the purple line is to the center, the higher the disruption. This glyph is based on the Z glyph by Cao et al., which has shown to be more effective over traditional glyphs for showing deviations from normal. A user can be selected by clicking on their circle and magnifying it in the magnified eyes of Argus view. Every underlying slice is one day, and the beige slices are weekends for added contextual information. Hovering over the slices shows the human readable date along with any participant reported information for the day. The most commonly occurring channel values are shown in an ordered list in the core currents view. Clicking on a list item shows the most commonly occurring channel values to help an analyst form quick associations between different channels. For instance, it is common for the phone to be both locked and charging for long durations at night. The duration view shows the total occurrences of specific channels throughout the ordered days. For instance, for how long the smartphone was locked, etc. The Y position of the horizontal line shows the average duration for the specific channel to allow analysts to make quick visual comparisons between days. The explainability view shows the raw sensor level data per day to explain behavioral rhythm breaks. The first line chart shows the average occurrence values per hour for the sensor channels, such as the phone being in a dark environment, charging, and having the screen locked. Each individual line chart after that represents the sensor values per hour for the days selected in the magnified eyes of Argus view. The geolocation data was clustered using the DBScan algorithm, and the colored bars atop the lines represent durations of time spent in different geoclusters, with the color encoding the human understandable category of geolocation, which we get from the Foursquare API for added contextualization. The positions of the sensor values along a common scale make it easy for the user to discern hourly changes. Now we will present some use cases. We used Argus to visualize the student-life data set, which contained smartphone sensor data for 49 college students collected over the course of an approximately 2-month-long academic term. The smartphone app they used continuously gathered sensor data passively. The datasets also contained contextual information about the various academic deadlines throughout the term, along with answers to daily questionnaires with wellness information like sleep quality, duration, and stress levels, etc. In this use case, the student had reported poor quality and a low number for the hours of sleep in days leading up to a day with due deadlines. The user can clearly see large breaks in rhythm, and overlaying contextual information helps the user explain potential causes of such disruptions. Small disruptions in rhythm are not concerning. The user needs to be able to contextualize such small disruptions to disambiguate them. The user notices a large break in U46's georhythm. The user clicks on the days, which happen to be Friday, Saturday, and Sunday, and notices from the bar over the sensor value lines that U46 was detected to be in a hotel during parts of those days. This contextualization helps a user disambiguate such a disruption. The user may also want to see the types of changes that occur in sensor values during stressful times. The user can see major disruptions in the rhythm for May 13th and May 14th, both with deadlines. The student was in a lab in the early hours of May 13th with almost no time spent in a dark place, and they also only had a few hours in early night where the screen was continuously locked. On May 14th, they were in a residential place for some time in the early hours of the day where they were in a dark environment and had their phone charging. The user is able to contextualize this large disruption in objective sensor data by providing multiple levels of human understandable information, which can lead the user to a more complete picture. In conclusion, we designed and developed Argus, an interactive visual analytics tool to find and explain disruptions in smartphone-sensed human biobehavioral rhythms. We validated Argus using real-world smartphone-sensed data.
I mean, great tool and very interesting connection to life sciences. So after looking through all this data, how can we improve our quality of life?
So the idea is that these systems, analysts would like to see data in these views to be able to design systems or applications that would lead to better context-aware computing. So things like having automatic apps deployed that can detect if you have issues with your sleep, and sending you notifications about changing your habits. And so the idea is that having all this very complex data is pretty hard to understand using just computation models. And then using data visualizations can help analysts come to more interesting conclusions that can lead them to design better solutions for context-aware computing.
Yeah. So that tackles definitely the analysis side of it. Just let us switch that around, okay? So in your work, you are focusing on these low quality ubiquitous sensors like smartphones, right? Let's switch it around. What would be high quality sensors that you would like to see for this kind of an application?
Well, so smartphones are never really meant to be like sensors as an important part of a smartphone, but they were never really meant to, perform long-term evaluations on people. In terms of, excuse me, in terms of high-quality sensors, it would require, things like actigrams, things like, putting armbands around people that have high-quality sensors. But the problem with that is getting data in the wild on a much larger group of people is actually quite difficult. So that's where smartphones provide their value. They are ubiquitous. Everyone has a smartphone, and they have sensors that are not very robust. But recent technological advances have meant that analysts are able to gather some pretty accurate contextual information that has health information in it. And so, these biobehavioral rhythms is just one part of that. There are other studies that show that, changes in your smartphone data can be indicative of infectious diseases. And so this is just one part of it. And moving forward, the idea is to have all these views that can let analysts develop more robust models to find more health-related data.
Very good. Thank you very much for this interesting paper. So we will switch over now to the sixth paper in this session, the design of real-time visual analytics support tool for conflict detection and resolution in air traffic control, something that people hopefully can do well. The presenter will be Amira Zorid-Bandi. The other authors are Carl Westin, Jonas Lundberg, and Anna Singerman. And with that, the stage is yours.
Hello everyone, my name is Elmira and I'm going to present to you the design study we conducted on a real-time visual analytics tool for air traffic controllers to support them in conflict detection and resolution. Currently, air traffic controllers solve four-dimensional problems on a two-dimensional situation display. The image you see now is a simplified version of the radar screen that I have simulated. As you can see on the left display, lateral separation is depicted by a circle around each aircraft, and on the right display, labels present which aircraft are in conflict and how close they will become laterally when separation is lost. While lateral separation is straightforward to determine visually on current 2D displays, vertical separation requires that the air traffic controller reads the flight level information in the flight label and develop a mental model of the vertical relationship between aircraft. This process is cognitively demanding, and recent research has shown that air traffic controllers often prefer vertical solutions, especially during urgent situations. The study we conducted builds on the basis of a rather long design process where many design options have been explored and tried out. The design process underlying the final version of the concepts presented in this paper has spanned design activities and iterative prototyping over 18 months. An expert air traffic controller with 14 years of experience as an approach controller supported the development process by providing domain-specific feedback on required information for the conflict detection and resolution task. The design process consisted of two major activities: an initial work domain analysis and an evaluation with air traffic controllers. The work domain analysis was conducted on a conflict detection and resolution decision-making task. The goal of this task is to ensure safety and maintain efficiency while promoting air traffic controllers' performance. To achieve this goal, the analysis revealed the need for visualizing core sets of information about conflicts: the aircraft pairs currently in conflict, time to conflict, horizontal and vertical separation information about current conflicts and potential conflicts. Detailed explanations on how I have modeled and formulated propagation of loss of separation based on which solution spaces were obtained can be found in the paper. Now I present to you the initial prototype developed for the visualization concept HTA-Viz, which stands for Heading Time and Altitude Visualization. On the left display, the colored and dark shaded circle sectors represent heading conflict zones. The dark shaded sectors represent heading zones for potential conflicts. Colors are used as a visual channel to encode linked aircraft pair, those that are in conflict with each other. The right display visualizes a novel concept named TA, which stands for time altitude. TA directs the focus on the temporal and vertical solution spaces of conflicts. We use the clock metaphor in terms of the well-known polar graph technique to highlight conflict urgency. In the polar grid, angular coordinate represents time remaining to a loss of separation, while radial coordinate with increasing radius represents increasing flight levels. The thick black line at 3 o'clock direction is a fixed reference line representing the time when separation between two or more aircraft is lost. The other black line, which in this picture directs towards blue and cyan aircraft pair, is always drawn for the most imminent conflict and moves counterclockwise towards the loss of separation line. Vertical profiles of conflicting pairs are visualized on TA with the same color as heading solution space. We evaluated the initial prototype with 8 air traffic controllers. The evaluation consisted of 2 parts, a quantitative study and a semi-structured debriefing. The 2 main independent variables of the quantitative study were conflict geometry and display condition. 4 display conditions were used: a control condition consisting of a conventional situation display without any visualization support for conflict solution spaces, and 3 treatment conditions depending on whether the heading solution spaces and TA visualization was enabled or disabled. Analyzing time for solving conflicts, applying Friedman's test indicated an effect for the urgent climb-descent conflict and a marginal effect for the non-urgent conflicts. The analysis revealed that the greatest benefit for solving urgent conflict pair was mainly attributed to visualization of heading solution spaces. That could be due to the fact that controllers had no experience from working with a display like the TA visualization. But this needs further evaluation studies. Several air traffic controllers requested a representation depicting how aircraft rate of climb or descent options affected the vertical solution space. They also claimed that collecting information from 2 displays were time-consuming, especially during urgent conflicts. Based on the outcome of the evaluation study, a composite glyph-based design was approached to provide a graphical representation of both horizontal and vertical solution spaces for the traffic situation in one single display. In this figure, you see the glyph for an aircraft located on the radial timeline with flight level circles depicted in the background. The green line inside the icon indicates heading. The red section on top of which the heading line is placed indicates forbidden heading criteria. Brown pattern sections indicate forbidden heading criteria for potential conflicts. The composite glyph contains 2 circles, an outer circle and an inner circle. On the outer circle, heading solution space is shown, while on the inner circle, rate of climb and descent solution spaces will be shown. The inner circle is split in half by a line which is aligned to radial timeline that the glyph is located on. The area behind the timeline is used to select the aircraft, while the area in front of the timeline shows the rate of climb and descent range. The black line aligned with the current flight level of the aircraft represents 0 rate of climb. The section faced at lower flight level represents rate of descent range, while the section faced at higher flight levels represents rate of climb range. The colorful line inside rate of climb or descent range shows current rate of climb. The line has the same color as the vertical profile line on TA as well as boundary of the outer circle. For this aircraft, the color is yellow. The colorful section inside the rate of climb or descent range represents forbidden rate of climb range. Now I present to you the final HTAViz design. 4 conflicts are now being visualized on HTAViz, of which 2 need to be resolved in less than 2 minutes. Both conflicts consist of a climbing and descending aircraft pair. Unlike previous designs that provide information about vertical solution spaces on demand, HTAViz visualize the information about conflict zones in real time without a need to click on individual aircraft. This is expected to reduce working memory load in terms of collecting and storing information in memory. We are currently conducting an evaluation study on the final design of HTAViz to explore the extent to which HTAViz affects controllers' way of problem solving and performance. Moreover, new versions for HTAViz will be explored where flight levels are shown with angles and time is shown with circles on polar graph. Implementing such changes make it possible to evaluate how the toroidal structure of the polar graph affects cognitive information processes.
Great. Thank you very much for this interesting talk. Maybe we'll open up here for questions. I see one coming in from Wolfgang Eigner. Which flight data was used for the testing?
Sorry, which flight level was it?
Which flight data was used?
Okay. We used a kind of well-created scenarios, but we conducted several studies where we consulted an expert air traffic controller. We consulted their opinion, whether the traffic scenarios look realistic or not, whether the conflict geometries look realistic, and they talked throughout the study with us which conflicts is good to put in scenario, which conflicts are critical, how the traffic situation looks usually to them.
Great, thanks for this answer. Wolfgang mentions it looks as if there are much more details included in the glyph visualization than the usually used one does. Does that mean that more space is needed when we zoom, or more zoomed in space?
We are currently conducting a full evaluation study on the final design, which includes the final glyph-based design that you just saw in the presentation. We have enhanced the interactive features where the controller can see the detailed glyph design once they, for example, hover the mouse over one specific aircraft. But in the previous prototype, it was easy to zoom in to see more details of the solution spaces. But we have further enhanced all these interactive features based on a qualitative study that we conducted after this design with one air traffic controller, and we consulted their opinion about the interactive features.
Great, thank you. With that, thank you, Elmira. And Jason writes here something very important, and I'd like to chime in here and read that out loud. Parallel coordinates and air traffic control in this session makes me want to shout out to Alfred Inselberg, who died last year, but left a lot of influential ideas to us and was always encouraging. So thank you, Alfred. With that, we are going over now to the best short paper, which is called Dissecting Visual Analytics, Comparing Frameworks for Interpreting and Modeling Observed Visual Analytics Behavior by Vanessa Brown, Chatagay Turkay, and Radu Jianu. Sorry for that. The stage is yours.
Welcome to our talk on dissecting visual analytics, comparing frameworks for interpreting and modeling observed visual analytics behavior. This is work done at City University. Welcome to our talk on dissecting Welcome to our talk on dissecting visual analytics, comparing frameworks for interpreting and modeling observed visual analytics behavior. This is work done at City University of London and Warwick University. I'm Radu, and I'll present this to you. Observation studies in Viz are important because they let us understand the visual analytics process and evaluate how visualizations and systems support them. And they typically look like this. You get a user in the lab and give them some data, visualization, and tasks to work with. You record them thinking aloud, their screen or ambient video, and take notes. And then you make sense of all of it, most often in Viz using thematic analysis. One or more researchers look at the data and through a controlled process identify common themes in the data. There's both a problem and an opportunity here. The problem is that this analysis is very dependent on the expertise of the coder. Often there's plenty going on during such a session: cognitive and perceptual processes, interactive visuals, data facets, and so on. A seasoned researcher is likely to pick out much more of this than, say, a new PhD student. The opportunity is that the HCI community has already worked on this. Specifically, they developed structured experimental frameworks that tell researchers what they should look out for when they interpret observation data, and they found that this structure leads to more complete and consistent analysis. So the idea behind our work was to see how well some such frameworks work for Viz. And here's what we did. We first ran an observation study to get some data to play with. The paper describes the study fully, but in short, we adopted a pair analytics setup. A data analyst and a domain expert spent about an hour using Tableau on a computer to analyze data provided by the domain expert. We ran 6 such pairs and recorded audio on screen and ambient video. We then used this data to evaluate what 3 established HCI frameworks can tell us about the analytic process. For the rest of the talk, I will briefly introduce these frameworks and tell you what we found helpful about them and what not. First, joint action theory, JAT, originally meant to explain how people coordinate joint actions, but was recently used in Viz by Arias Hernandez and Castro et al. To study how pair analytics works. From our understanding, applying JAT to pair analytics looks like this. We search our data for vertical markers, which are speech or body movements which mark changes in the analytic process. For example, our participants would lean back in their chairs to discuss and conclude a particular finding. Then they would lean back in to focus on something new. Such vertical markers help us break down a long analysis into smaller parts. Once the analysis decomposed, the assumption is that the different lines of reasoning become apparent, and we should be able to describe the role of each part in the analysis as a whole. Additionally, if we are interested in the collaborative aspect of analysis, we can also look for horizontal markers, small nods, or self-talk, which explain how joint awareness is built, how the pair stays on the same page. We applied this process to our data and found that, indeed, vertical markers help us decompose analysis into smaller parts. However, we were then left to our own devices to interpret them, and this was not trivial. Moreover, JAT doesn't provide any way to capture how visualization supports or even drives analysis. So ultimately, we felt that JAT might be good at explaining how people communicate, but it didn't really provide enough guidance to support an insightful analysis of data. Next, we tried distributed cognition, DC, which sees cognition as not confined to a person's head, but rather distributed, arising from how people work together and with physical and digital objects. The idea that we could use DC to model visual analytics has been acknowledged in Viz, albeit not extensively. However, what hasn't received too much attention is its use as a tool to interpret observation data. DC can be studied because all the processes are observable. We can listen to people talk, see what they do on their computer, and so on. HCI has really latched onto that benefit and evolved frameworks for studying distributed cognitive systems. For example, Hutchins tells us to pay close attention to the components of the studied cognitive system, how the information flows between those components, and the physical and digital artifacts and how they aid cognition. Similarly, Blandford and Furness's DICOT framework describes 18 principles grouped into 3 facets that researchers should mind when observing collaborative work. For example, they should be looking for information hubs, that is, when information is pooling, where and how people access it. Or they should be looking for scaffolding artifacts, which are physical or digital props for people's cognition. Turning to our data, paying attention to these essentially themes from DC and DICOT seemed useful. Most importantly, the artifact angle seemed perfectly suited to describe how Tableau supported cognition. Now, DC and DICOT's principles relating to artifacts were slightly vague, so we also referred to literature on external cognition, which is a whole area on how cognition, perception, memory can be extended by external props. And this led to quite insightful observations. For example, tabs in Tableau scaffold both memory, or analysts use them to trace their analysis and refer back when needed, but they also scaffold perception and cognition, because one can toggle back and forth between 2 tabs to compare things. So we found DC plus DICOT plus EC, external cognition, to be quite strong at explaining how visual tools extend the user's cognition. The thing that was lacking, though, was that there was still no guidance about interpreting how the analysis process unfolds. Are we in an exploration stage or a confirmatory stage? What prompted an analysis path? So experimenters are still left to their own devices when explaining this kind of analysis flow. Finally, situated cognition says that the way people pursue their goals depends largely on the affordances and constraints that the environment suggests to them. For example, I land at the London airport and would like to transfer downtown, so I become attuned to things that will further that goal. For example, I spot a railway ticket machine. This is an affordance, it suggests a course of action. I go by train. My goal now changes to buy a ticket. I approach the machine, see no keyboard, so I touch the screen to interact with it. The absence of a keyboard was a constraint, but it also suggested a course of action. So little by little, broader goals translate into more specific goals, and the environment directs my actions by suggesting possibilities and constraints. This explained well some of our data. Our analyses were often determined by affordances and constraints within Tableau, and this is different from studying regular interfaces, data affordances and constraints. For example, most analysts relied on Tableau's visual marks and encodings, and often cycled through them to see which one was informative. The ability to drop multiple dimensions in here also determined the kind of visualizations that were pursued. On the other hand, a few domain experts asked for text analysis, but that wasn't explored since our analysts didn't know how to pursue that in Tableau. Or, domain experts asked to combine data dimensions together, and that was pursued but rarely, as it involved typing in sometimes complicated formulas. Similarly, some pairs were cycling through data dimensions until finding something surprising, which then made them think about other, perhaps related dimensions to explore. And we would call this a data affordance. In general, we found situated cognition quite promising in explaining how analysis is pushed forward by users' goals, but also data and tools. However, I do note that most of our analyses were exploratory and thus more prone to be guided by the visual tools and the data, than perhaps confirmatory analyses, for example. So, our takeaway on these three frameworks and their use in Viz. Joint action theory may explain aspects of collaboration, but does not offer much for describing the analysis process and how Viz supports it. Distributed cognition, especially with a focus on external cognition, captures how Viz and systems support users, but doesn't help with describe the analysis process. Situated cognition explains how analysis, at least exploratory analysis, gets shaped by goals, data, and tools. Overall, we feel there's more space for research here, perhaps in putting together a framework that is tailored for specific use in Viz, but also just more observation studies that go beyond thematic analysis. Thank you.
Great work. I really liked it. The paper is really well written, and I can all point you to this paper for sure. It opens also up a new view, especially for the young researchers, what really is there as an overlap between HCI and, for example, the vast domain. So Wolfgang Eigner asks, would you suggest to combine some of the presented approaches in some way?
Yeah, certainly I think that's, so there are two aspects here. Depending on exactly what you study, you can pick one or the other that suits the goal. So if you're studying how visualization supports cognition and drives the process perhaps, or rather how it supports cognition, then you might go for distributed cognition. If you're really interested in how the process unfolds and what drives different analysis directions, then perhaps situated cognition and something else that we haven't studied in this paper might work better. If you want a more overarching framework that young researchers could latch onto, so that they don't have to jump back and forth between these different frameworks, then we would probably need to develop something that's more specific for visualization and incorporates bits and pieces of all of these different frameworks.
Okay, thank you. I'm skipping one of the questions in the YouTube chat for the second one that is a little bit more provocative, right? Now what? How do we move forward?
So I think my previous answer suggested one direction to that. So I think it would be beneficial to, so there are two things. We should look at more of these frameworks. We've evaluated 3, but there was scope for more. There's, for example, a paper in the Viz literature from, I think, 2018 or 19 by Lam et al., who are looking at precisely what some of these frameworks lacked, which is describing or detailing what each analysis part is meant to do or what its goal is. So exploring more of these frameworks is another step, is one of the first steps. Then coming up with a framework that is more dedicated for Viz would be another. And then I think simply running more of these observational studies and interpreting data using these more structured approaches would be a third direction that I could see things going in.
Great, thank you. Very important work. I have to restate that. Thank you for this work. So, which brings us now to the last paper in this session, which is examining design-centric test participants in graphical perception experiments. The authors here are Grace Wu, Yankee D, Nazim Ibrahim, Sam Joyce, and Ante Orthuis. Without further ado, here we go.
Hello everyone, my name is Bianchi. I'm a researcher at the Singapore University of Technology and Design, and I'll be presenting on behalf of our team at this session. In this paper, we replicated Cleveland and McGill's as well as Hiren Bostock's work on graphical perception. However, we used participants recruited from design-centric professional networks and university programs in Singapore, in contrast to the volunteers for Cleveland and McGill's pen and paper study and the Mechanical Turk workers in Hiren Bostock's web-based experiment. As for the reason behind this replication, we all know visualizations are a useful tool in many contexts. That's why we're taking part in this conference. They play a key role in exploring and analyzing data as well as in decision-making. However, there's relatively little research on exactly how visualizations are read and used to generate actionable insights in decision-making processes. And despite overall attention to this interaction between visualization and decision-making, especially in cartography with Jack Berton's Semiology of Graphics and Color Brewer by Cynthia Brewer, empirical and experimental visualization research has, for various reasons, focused on the assessment of relatively narrow and specific tasks. These are often tested with specific convenient respondent populations, as we see in Cleveland and McGill. So there are similar studies that assess graphical perception, but that use participants from Amazon's Mechanical Turk, or MTurk for short. These include Hiren Bostock's replication study of the original work by Cleveland and McGill, Talbot's and Lorena Nunn's expansion of the bar charts experiments from Cleveland and McGill, Scow and Casaro's study on the contentious pie chart and its variations, and Kim and Heer's work into the combined effects of visual encodings and data distributions. So such studies tend to draw their test subjects from the researchers' university students or other convenient participant populations like MTurk. But this issue of test populations has been well documented and critiqued, especially in psychology, mainly under the label weird. In short, people from Western educated, industrialized, rich, and democratic backgrounds may not be representative of all people. And in the context of this research, undergraduate students or previous work on Mechanical Turk may not be representative of professionals and decision makers. This is a potential issue if we design visualization systems for decision-making for specific domains based on recommendations derived from empirical research on such groups. So it's part of the impetus of our research here in this paper that student populations commonly used as research participants in visualization research may not be representative of the larger population, or in our case, of decision makers specifically. Furthermore, we want to learn if spatially trained design professionals may be better at reading certain charts than others. Thus, our primary goal was to assess the potential effect of different participant backgrounds on graphical perception, specifically students versus design professionals, and to which chart types these were applicable. So for our experiment, we performed a replication of Cleveland and McGill's and Hiren Bostock studies with two populations, students, design professionals. We replicated both studies' tests on proportion estimation across different spatial encodings, position, length, angle, area, and we used the same charts as Cleveland and McGill, types 1 to 6, and added the tree maps from Hiren Bostock, type 7. The student group that we recruited were composed of students currently undertaking architecture and engineering courses at SUTD. The design professionals were recruited through design networks, including the National Design Council of Singapore. So this includes professionals from fields like architecture, product design, and others. We collected responses through a dedicated web platform developed for this experiment, and through specific invitation links generated for each group. This allowed us to track the status of different groups individually. We had a total of 123 respondents, with 87 students and 36 professionals. Each participant was asked to respond to 42 questions in random order. Each question consisted of a unique chart belonging to one of these 7 chart types, and each chart had 2 colored segments, one blue, one yellow. Participants were first asked to indicate which segment was larger by choosing the color of the segment, and then asked to judge the percentage the smaller segment was of the larger segment. To assess performance, we adopted the same assessment measures for accuracy, log absolute error, and response time, the natural logarithm of this difference, as these two previous studies. To test between group differences, we use ANOVA and followed up with 2 key post hoc tests. Our results generally replicated earlier studies and the order of performance among the charts, surprisingly. We found a significant effect of chart type on response accuracy and a similar order of accuracy between the chart types as in Cleveland and McGill and here in Bostock. Bar charts, specifically type 1, were the best performing, and tree maps, or type 7, performing the worst for accuracy. Overall, all chart types significantly differed from each other for accuracy. We also found a significant difference in response times between charts. Response times were similar between types 1, 2, and 3, all bar chart variations. Type 2 bar charts were the fastest with 9.2 seconds, while tree maps were 30% slower with 12 seconds. We also observed very weak to no relationships for correlation between log error and log time taken for all charts. This is on the right. This suggests that taking more time to respond does not significantly alter the accuracy of the judgment, regardless of chart type. As for the effects of occupation on chart reading performance, we found no significant effect of occupation on accuracy, as seen on the left-hand side charts. Even when we analyzed the difference in accuracy between students and professionals for all chart types, none of the differences were statistically significant. This suggests the relationship between visual encodings and reading accuracy is not sensitive to sampling bias present in many empirical designs previous. However, we did find a significant effect of occupation on response time taken, which clearly appears in this violin plot of the response time for each group on the left. On average, students take about 2 seconds faster than professionals. This can have a host of different reasons that we can explore in future work. Perhaps students felt more rushed or more comfortable with digital tests. And on the right, apart from our results of her chart types and occupation, we also found that the observed errors have a relationship to the actual true difference between the 2 segments that the respondents are asked to compare. Overall, mean error decreases if the difference between these 2 segments increases. This suggests participants find it more difficult to accurately estimate the difference between 2 segments as the true difference between them increases. We also note that the error variance, if you look at the extremes of this chart, are noticeably higher for both very small and very large differences. In summary, we replicated earlier empirical studies and the results on graphical perception of different visual encodings successfully. We tested 2 different groups, students and professionals in Singapore, to evaluate the effect of participant background on graphical perception. Surprisingly, our findings did not show any significant difference in terms of reading accuracy. However, we do observe a significant difference in response time between the 2 groups, with students being significantly faster. In summary, theoretical principles from visualization theory and recommendations from previous studies on the accuracy of different visual encodings could potentially apply beyond the often used populations of students and MTurk workers. However, as is indicated by our findings, specific subgroups such as design professionals and other decision makers may indeed read visualizations in slightly different, nuanced ways. And that's all from us. Thank you for your attention. We look forward to your questions.
Great, thank you. We are open for questions in the YouTube chat or in the Discord. And while we are waiting, let me ask this question, right? This work made me think a lot about visual literacy, and there is some important work in the direction here, especially from the INRIA group. Now to my question. How can we better educate people to read visualizations? And the more critical question for me is that an offline task or is that an online task while they're using the tool?
That's a really interesting question. Visual literacy is something that's even more important nowadays with the amount of news that each of us gets, and each and every person can make their own charts, so there's a lot of tools available. I feel that this is both a question, that this is both something that can be addressed online and offline, both in print and digitally. Though, of course, there are certain things that digital mediums allow us to do very well, such as interactivity, that better support visualizations. But even basic things such as reading off bar charts or reading off line charts are really crucial, and I think it really starts in school, like not just at university, but even from a younger age. I feel that this is a crucial part of, well, being able to critically think as well, which is to be able to interpret visualizations and what they mean and whether what they're trying to say actually is speaking of the data that it was sourced from, or if the people who created the visualization are trying to say something else completely different.
Yeah, I fully agree. I fully agree on that point. So there are questions tickling in, but in the interest of time, I just want to ask a very short one from Tatjana Franzberger. What are the age groups of students versus the professionals?
So the students skewed a lot younger. So I would say that they were in the age range of around 18 to late 20s. And then in some cases, we did get a few early 30s because we did have master's students in our group. And then for the professionals, they were mid-20s to above, basically, until the retirement age, which is around 62 in our test population.
Yeah. And interesting is that aspect that they answered pretty fast in comparison to each other, right? There was a clear difference. This is
yes.
We are training our students to answer fast.
Yeah, that could be a reason why we got these results. That the students nowadays are, as we've noted, maybe more visually literate than those that came before them, and it just makes clear that visual literacy is something that needs to be worked on very early on.
That's my point as well. So I see two other questions. I ask you please to restate them over in the Discord channel. And I would like to thank you for your time in this interesting presentation. And with that, we are done with this session. We had in peak time 65 viewers here. And sorry for the technical difficulties that we had along the way. I'm pretty happy how this all went. And with that, I would like to thank the organizers for this really immense efforts that they took here. And the second set of people that I would like to thank are the authors and the speakers over here. So big clap for that. And also the audience for asking these interesting questions. Last but not least, the next session starts at 1:30 with two keynotes, one industrial keynote and one this keynote. And with that, thank you very much for your attention and see you around here in the online conference.